So, when most people picture how a car is made, I mean, the mental image is almost always exactly the same,
Yeah,
right?
sparks flying everywhere.
Exactly, sparks flying, these massive steel presses stamping out metal. It's just heavy machinery inching along this endless conveyor belt.
It is, it's like the ultimate definition of heavy industry.
Right. And historically, an automaker designs a vehicle, they spend, hundreds of millions of dollars retooling a factory, and then, well, then that exact model just sits on the dealer lot, basically unchanged for 5 to 8 years.
Yeah, a 5 to 8 year cycle. I mean, it's a glacial pace of evolution, but by design. A
Yeah.
2-ton piece of machinery historically required that kind of rigid, unyielding production cycle, just, to ensure basic safety and reliability.
But consider what happens when you stop treating a car like a piece of heavy machinery and start treating it more like, I don't know, like the smartphone in your pocket.
Right, where the hardware is just a vessel for the software.
Exactly. You wake up and an over-the-air update has completely bypassed a hardware limitation. The operating system is entirely different. The paradigm has just shifted overnight.
It really is.
So, welcome to the deep dive. Today, our mission is to explore exactly how the traditional automotive industry is being turned on its head at just this dizzying speed. I mean, shrinking a century of innovation into mere months. And most importantly, what that actually means for you as a consumer.
Because we are looking at a roadmap here that connects vehicle manufacturing, global energy grids, and high-level enterprise technology into one continuous loop. It's all connected now.
It is, and we
Right.
have some incredibly rich source material guiding us today. We're pulling from two highly detailed innovation papers, specifically parts 2 and 3 of the Future of Mobility series.
These are fascinating documents, by the way.
They really are. They were recently published in the UK Salesforce Consultants and Contractors community on LinkedIn. And for those of you familiar with that space, you'll know it as the SFC&C community.
Right, a very active group.
Yeah, and the founder of that community, Dovydas Mockevicius, actually authored these papers. We are also looking at his Salesforce Trailblazer profile just to kind of understand the unique lens through which he is viewing these massive industry shifts.
And honestly, the background of the author it's actually the key to understanding this entire transition.
How so?
Well, usually you'd expect, like, a mechanical engineer or maybe a supply chain analyst to write an innovation paper on the automotive industry, right?
Right, a traditional car guy. But looking at Dovydas' Trailblazer profile, his background is pure enterprise architecture. I mean, his credentials are staggering.
Really are.
He is the CEO of Ice Cloud, a seasoned CXO, and an enterprise architect based in the UK. We are talking about a professional with 17 Salesforce certifications.
17 is, I mean, that's wild.
It's a lot of studying. 13 of those are in the Salesforce platform alone, plus Sales and Service Cloud and CRM Analytics. He holds 2 super badges, a massive 248 Trailhead badges, and he earned the title of 2025 Agent Blazer Champion.
Which, brings up a really fundamental question for the listener. Why is an enterprise tech specialist, someone with deep expertise in cloud platforms and data analytics, analyzing the future of electric vehicles?
Yeah, the connection might not be immediately obvious.
Exactly. It seems like two completely different worlds.
But I look at it this way, and tell me if you agree. Modern EVs simply aren't just cars anymore. They are essentially highly complex, rolling enterprise networks.
That's spot on.
I mean, if a car's sensor detects a slight voltage drop in a single battery cell, it doesn't just turn on a dumb dashboard light anymore. That car pings a centralized cloud system. It logs the anomaly in a customer relationship management platform like Salesforce. It checks global supply chain inventory for a replacement part. And it literally schedules a service appointment for you before you even know there is a problem.
Yeah. And that mechanism, that is system-level integration at a massive scale. To scale an electric vehicle business today requires the exact same skill set as executing a massive digital transformation or, a really complex management consulting gig.
It's not just bending metal anymore.
Not at all. It requires master-level enterprise architecture. An EV today is thousands of data points, real-time analytics, supply chain logistics, all talking to each other instantly. The software and the overarching digital systems, they entirely dictate whether the hardware succeeds or fails.
Okay, so let's transition from that enterprise mindset into the physical product itself, because part 2 of the paper declares the traditional 5 to 8 year automotive life cycle completely dead.
Dead and buried.
The stat that really jumped out at me is that development cycles have shrunk down to just 3 to 9 months. We are seeing some EV models getting 2 facelifts a year.
2 a year. I mean, if a manufacturer is retooling or updating every 6 months, their software and hardware integration must be absolutely flawless.
There's no margin for error.
Right. They simply cannot afford the traditional delays of physical prototyping. They have to run it like a software sprint.
And this hyperfast cycle leads to what the source outlines as the gold standard for a 2026 EV. He lists a few key specs that are just mind-blowing.
Let's hear them.
First, a 1,000-volt architecture. For context, 800-volt systems were cutting edge just recently, but now cars like the Leapmotor D19 are pushing 1,000 volts.
And structurally, mechanically, higher voltage means the vehicle can use thinner wiring, it generates less heat, and crucially, it can accept power much faster.
Right. He also projects over 650 kilometers, which is about 400 miles of range as standard.
But the most disruptive spec in that gold standard, I think, is the charging speed. The projection is a charge from 10% to 90% in under 10 minutes.
Under 10 minutes. That's getting really close to the gas station experience.
It is, and it's utilizing what is known as 15C charging.
Okay, let's define 15C for you listening, because that term gets thrown around a lot in these engineering papers, and it can be confusing. The C stands for charge rate.
Right.
A 1C rate means it takes exactly 1 hour to charge a battery completely. So a 15C rate means charging a battery in 1/15 of an hour.
Which is incredibly fast.
1/15 of 60 minutes is just 4 minutes. So we are talking about dumping massive amounts of energy into a car in roughly the time it takes you to walk inside and buy a coffee.
And achieving that speed, it requires a total overhaul of the physical vehicle structure. The paper highlights several manufacturing shifts driving this, including gigacasting and ether loop wiring.
Yeah, let's break those down. When I hear gigacasting, it honestly sounds like science fiction. But it is a very real, very brute force manufacturing technique.
It really is brute force.
Instead of stamping out, 100 individual pieces of steel and having robots slowly weld them all together to form a car's frame, gigacasting injects molten aluminum into one massive house-sized mold.
It just presses it all at once.
Yeah. It produces a single solid piece of the car that saves an immense amount of time. It drastically reduces the factory footprint, and it cuts the vehicle's weight.
And then on top of that, there's ether loop wiring.
Right. Explain ether loop.
So, modern cars are currently bogged down by literal miles of heavy, analog copper wiring harnesses. They connect every single window switch and temperature sensor.
It's a mess of cables.
Exactly. Ether loop is essentially replacing all that thick point-to-point analog copper with a centralized, high-speed Ethernet-style network. Less copper means a significantly lighter, smarter car.
And the weight reduction strategy goes even further, which blew my mind. The introduction of in-wheel permanent magnet motors combined with structural battery packs.
This is a massive shift.
I really pushed back on this when reading the source material at first. I was like, wait, moving the actual motor out from under the hood, removing traditional axles and heavy brake calipers, and putting the entire propulsion system inside the wheel hub itself.
It sounds like concept art for a sci-fi movie.
Right. I was like, does this actually exist? But looking at the data, companies like REU Automotive, Honey Mobies, and Todian Electric are actively building this right now. It is a reality.
And the engineering logic behind it is just compelling. By moving the motors to the wheels and utilizing structural batteries, which, by the way, means the battery pack isn't just a heavy box sitting inside the trunk.
Right, it's actually part of the car.
Yes, it actually forms the physical load-bearing floor of the vehicle itself. And by doing that, manufacturers are stripping out 200 to 500 kilograms of dead weight.
That is half a ton.
Yeah. And these condensed structural packs are safely hitting energy densities of 250 to 300 kilowatts per kilogram.
So if you cut 500 kilograms of material out of a vehicle, you are drastically cutting the cost to build it. The paper states this reduces production costs by roughly 50%.
50% is a game changer for the market.
It's huge. When you slash the manufacturing cost in half, the impact on your wallet as a consumer is monumental. Dovydas maps out this target consumer impact, saying smaller vehicle segments will be dropping to the $10,000 to $25,000 mark.
Which makes EVs accessible to almost everyone.
Right, and mid-size SUVs dropping under $40,000. Plus, with the motor inside the wheel and a solid-state structure, there are just vastly fewer moving parts to break, and that is driving manufacturers to offer 8-year to even lifetime warranties.
A hyper-efficient, highly durable vehicle at a fraction of the historical cost. I mean, it sounds perfect.
It does sound perfect.
But, however, The physical vehicle is only one half of the mobility equation. The fastest charging battery in the world is completely useless if the infrastructure supplying it creates a bottleneck.
Which brings us to the grid problem outlined in the sources. We have the technology for this 15C ultra-fast charging inside the car, but the moment two or more of these vehicles plug into a standard station at the exact same time, the local power grid throttles the performance.
It just can't handle the draw.
No. I think of it like an old residential water system, right? If one person opens a fire hose, they get massive water pressure. But if 10 people open fire hoses on the exact same street, the pressure just drops to a trickle.
That's a great analogy.
Thanks. The national power grids were simply not built to dump a massive, instantaneous spike of energy into multiple vehicles simultaneously.
And upgrading the entire global electrical grid to handle those spikes by 2026. That is an impossible task. We don't have the time or the copper.
Right. So what's the workaround?
The infrastructure solution required a totally different approach, which the paper details. It's the deployment of on-site commercial batteries at the charging stations themselves, which is a concept really pioneered by companies like FreeWire.
The mechanism here is brilliant. So instead of the charger pulling massive voltage directly from the city grid the very second you plug in your car, the station has its own large battery sitting there.
Exactly.
A buffer.
Yeah. That station battery slowly and steadily pulls a low amount of power from the grid 24 hours a day. Then, when your car pulls up and demands that ultra-fast 10-minute charge, it pulls that massive energy dump from the station's localized battery. It completely bypasses the limitations of the city grid. Because the constraint on electric vehicle adoption, it's no longer battery chemistry in the car. It is speed to market for this specific localized infrastructure. The scale of deployment is the new competitive battlefield.
And the paper points to BYD's aggressive deployment numbers for 2026 to really illustrate this scale. They're looking to deploy roughly 20,000 of these up to 15C charging stations in China alone.
20,000 in 1 year.
Yeah. Globally, they are planning an additional 6,000 stations. That includes 3,000 across Europe, for roughly 300 localized right in the UK. And remember, each of these stations features multiple individual chargers.
It's massive. And when a single manufacturer begins deploying infrastructure at that kind of scale, it forces us to zoom out and look at who is actually controlling the global market.
Right, the geopolitics of it all.
Exactly. Part 3 of Dovydas' paper transitions from the raw technology to the geopolitical realities of 2025, which is a year that fundamentally reshuffled the entire industry.
Yeah, and reporting impartially from the source material here, 2025 was truly defined by major disruptions. The United States elected a controversial president, Elon Musk entered the political arena, and Tesla faced a lot of global backlash.
It was a chaotic year for the market.
It was. And the source notes that the U.S. administration shifted federal policy away from clean energy and back toward fossil fuels. This included canceling EV incentives, rolling back carbon credits, and causing many domestic auto companies to pause or completely reprioritize their EV programs.
And all this occurred against the backdrop of a global tariff war that severely disrupted international business operations.
But the paper highlights a stark contrast here. While the U.S. market retracted and reversed course, the global balance of power shifted entirely.
BYD actually overtook Tesla in global sales.
Yeah, the concept of made in China really cemented itself as the indicator of high-tech dominance in the mobility sector. The numbers provided in the paper are just stark. Roughly 70% of all EVs globally and 70 to 90% of all battery manufacturing now originate in China.
And that immense concentration of manufacturing power has driven costs down to an astonishing degree. Battery costs in China plummeted to under $45 to $50 per kilowatt hour.
That's incredibly cheap.
It is, and they have a stated target of driving that down even further to just $19 per kilowatt hour. For context, the global blended cost across the rest of the world remains well over $90 to $100.
Wow. So if one region is producing denser, safer batteries at less than half the cost of everyone else, that ultimately dictates what kind of car you will be able to afford in the near future.
Exactly. Western competitors cannot simply wait for prices to stabilize or for a normal market cycle to turn in their favor.
Why is that?
Well, the expert analysis here points out that this cost advantage is structural, not cyclical.
Break that down for us. What's the difference?
Sure. A cyclical advantage means prices are temporarily low due to, say, market fluctuations or temporary subsidies.
Yeah.
It'll eventually bounce back. But a structural advantage means the fundamental architecture of the business itself is just inherently cheaper.
Ah.
The dominant players now own the entire vertically integrated value chain. They secure the raw lithium from the ground, they refine it in their own facilities, they manufacture the battery cells, they build the vehicle using that gigacasting we talked about, and they manage their own global shipping.
They own every step.
Right. When you control every single node of the supply chain, global competitors who are relying on a bunch of fragmented third-party suppliers, they simply cannot compete on price.
That makes total sense. So we have shrinking development cycles, we have localized grid bypassing chargers, and a geopolitically dominated battery market.
But there is a foundational layer beneath all of this.
Right. The EVs and their batteries, they are essentially just storage mechanisms. They are empty vessels until they are filled. Where is the actual energy coming from to power this massive global transition?
This is where it gets really interesting. The paper expands beyond the vehicles themselves to address the generation of power. In 2025, the global energy landscape saw the addition of 800 gigawatts of solar power.
800 gigawatts in 1 year.
Yeah, and the regional breakdown reflects that same geopolitical shift we just discussed. 370 gigawatts of that total were installed in China alone, while the EU installed almost 70 gigawatts.
And the technology behind that solar generation is also advancing rapidly. Dovydas notes the breakthrough of perovskite solar cells, making it to marketable dimensions and hitting 33% efficiency.
Which is a big leap from older panels.
Yeah. To explain why that matters to you listening, traditional silicon solar panels are thick, they are rigid, and they honestly have a fundamental physics limit on how much sunlight they can actually convert into electricity.
Right, they max out pretty early.
But perovskite relies on a completely different, highly efficient synthetic crystal structure. They can be made incredibly thin, practically printed on flexible materials, and they capture significantly more usable energy from the exact same amount of sunlight.
And look, more efficient solar generation is crucial for the immediate term. But the paper also highlights a longer-term systemic shift. The author refers to it as a slower tectonic plate that will move the entire global economy.
And that tectonic plate is fusion energy.
Fusion.
Yeah. Fusion is literally the holy grail of energy generation. It is the exact process that powers the sun-forcing atoms together to release immense amounts of energy, but without generating the long-lived radioactive waste that's associated with traditional nuclear fission.
Right, but how does fusion actually play into a 2026 EV market?
Well, the source material tempers expectations slightly here, noting that fusion is unlikely to make a significant global impact before 2035. So no, it won't be charging a 2026 EV.
Okay, that makes sense.
However, the milestones leading to that reality are imminent. The paper points to actual progress from entities like Commonwealth Fusion Systems and ITER, indicating that by 2030 we could see commercially viable fusion energy output.
And the implications of that 2030 milestone are staggering. The prediction is a 2 to 10 times decrease in global electricity prices.
A 10x drop. Just wrap your head around that.
It's wild. When the core commodity that powers civilization drops in price by a factor of 10, it completely rewrites all the rules. Artificial intelligence, massive enterprise data centers, global mobility networks, they all run on electricity.
If electricity becomes incredibly cheap and practically abundant, the pace of human innovation just accelerates exponentially.
It does. And putting this massive global narrative back to a localized perspective, the paper specifically examines the UK, which is Dovydas' home base.
Right. How are they handling all this?
Well, despite a really growing adoption rate for EVs, the UK is navigating deep structural challenges and declining productivity. The local execution is frankly lagging behind the global technological pace.
But he identifies a massive untapped opportunity for the region in the paper. The UK has the potential to mass deploy these new high-efficiency solar systems to households at a very low cost. It is a chance to cultivate local innovation and create homegrown energy solutions rather than just, passively importing all this technology from abroad.
And executing that local deployment brings this entire conversation full circle.
Back to enterprise tech.
Exactly. Navigating a hyper-fast transition that involves coordinating local solar generation, localized battery buffers at charging stations, and millions of connected vehicles. It requires masterful enterprise technology.
It requires the exact skill set we discussed at the very beginning of the deep dive. You need robust digital platforms capable of handling massive, real-time data flows from the cars to the grid.
You absolutely do.
You need to optimize complex supply chains and manage seamless customer experiences. Platforms like Salesforce and expert consultancies like iCloud, they serve as the vital digital glue holding all this physical infrastructure together.
Because it is no longer just about building a physical machine. It is about architecting the digital ecosystem that allows that machine to operate within a constrained grid.
Right. The overarching takeaway from these innovation papers is that the transition to electrification is no longer a story about early adopters or government policy support.
No, those days are gone.
It is a story characterized by brutal industrial scale, extreme cost compression, and the absolute necessity of system-level digital integration. We have covered an immense amount of ground today.
We really have, from hardware to software to geopolitics.
Yeah. We started with the realization that car development life cycles have compressed from years to mere months. We explored the engineering mechanics behind 1,000-volt architectures, gigacasting, and the weight-saving brilliance of in-wheel permanent magnet motors.
The 15C charging infrastructure battle, too.
Oh, absolutely. Understanding how localized batteries bypass the limitations of city power grids. We navigated the stark geopolitical realities of 2025, detailing how structural, vertically integrated monopolies in battery manufacturing have completely reshaped global pricing. And finally, we saw how enterprise architecture is the mandatory foundation for managing this hyper-complex transition.
It's a lot to process.
It is. So, as we conclude this deep dive, I want to leave you with a final thought to ponder, building on those fusion energy predictions we talked about. If we do hit that 2030 milestone, if fusion becomes commercially viable and the cost of global electricity truly drops by a factor of 10, making the energy required to move anything incredibly cheap, how does that change the physical map of your life?
Oh, that's a fascinating question.
Right. If the cost of crossing a physical distance is practically zero, how does that change where you choose to live, where you choose to work, how far you are willing to travel on a daily basis? Suddenly, the heavy, slow-moving constraints of the past look very, very different. Thank you for joining us on this deep dive. Keep questioning the world around you, and we will catch you next time.